Beneath a sky without birdsong, before forests and flowers, before even the earliest crawling creatures, our planet was already alive with subtle rhythms. Imagine oceans stretching endlessly, their waters tinted green with minerals and stirred by unseen tides, while continents young and restless shifted slowly in silence. This was Earth long before it became the world we know. No, this is a story of ancient worlds and quiet transformations, of a planet awakening in silence. And if you crave histories that lull you into peaceful dreams, subscribe now to the Faded Clock. The Proterozoic Era begins around 2 to 5 billion years ago, carrying us forward to 541 million years ago. It spans nearly half of Earth's entire history, yet it is often the least remembered, a hushed chapter between the fiery youth of the Archean Aeon and the explosion of visible life in the Cambrian. Scientists from institutions such as the Smithsonian remind us that this aeon was not empty, not forgotten. It was an age of patient preparation, of atmosphere and oceans quietly changing, of life slowly learning new tricks, of oxygen gradually filling the skies. Picture Earth's crust cooling, its plates shifting with slower rhythm than in earlier times, its volcanic breath steady but less violent. Supercontinents like Nuna and later Rodinia assembled and drifted apart, their colliding edges raising mountain chains that would erode into dust, feeding the oceans with nutrients. Though these names, Nuna, Rodinia, sound ancient and mysterious, they are constructs of human science pieced together from rocks scarred by unimaginable pressures, their minerals aligned like whispers pointing to long-vanished geographies. In this age, the air was different. During the Archean, oxygen had been almost absent, a trace gas at best. But in the Proterozoic, something profound occurred. Cyanobacteria, microscopic architects of transformation, began to flood the world with oxygen through photosynthesis. Geologists call this the Great Oxidation Event. It was not sudden, not a burst, but a drawn-out change over tens of millions of years. Oxygen first poisoned many earlier microbes, organisms that had thrived without it, leaving behind strange, rust-red bands of iron in ancient rocks. These banded iron formations, stretching across old seabeds, are among the most striking geological signatures of the Proterozoic. They remind us that oxygen, so vital to us now, was once a disruptive toxin. The seas of this time were alive, though not yet with fish or corals. Instead, they swirled with microbial mats, layers of bacteria and archaea woven into thin, living carpets upon shallow seafloors. These mats built stromatolites, stone-like domes formed as sediments stuck to sticky microbial layers. If you visit Western Australia or Shark Bay today, you can still see living stromatolites, silent descendants of those ancient builders. They stand as monuments to persistence, slow-growing but eternal-seeming, guardians of memory from Earth's earliest days. Above, the skies shifted hue. With oxygen came ozone, a shield against the harsh ultraviolet light of the sun. Slowly, the planet became safer for more complex life to evolve. Still, time moved at an almost meditative pace. Hundreds of millions of years passed where changes were incremental, hardly noticeable in a single lifetime but profound across eons. Imagine the silence, waves lapping shores that no animals yet walked, winds moving across continents where no forests grew, rivers running without witness, clouds forming over empty lands. In these long passages of time, Earth knew glaciations, great ice ages that wrapped its surface in white. The snowball Earth hypothesis suggests that, during certain intervals of the Proterozoic, ice reached even the equator, covering nearly the entire globe. Imagine a planet of gleaming brightness, oceans sealed beneath frozen lids, continents blanketed in silence. And yet beneath the ice, microbial life endured, clinging near hydrothermal vents, hiding in thin cracks of open water. These small survivors kept the thread of life unbroken. When the ice relented, oxygen levels continued to rise. The oceans, stirred by glaciers and enriched by nutrients, became laboratories for new experiments. Cells began to evolve complexity. According to the fossil record, it was in this era that eukaryotes emerged, cells with nuclei, the ancestors of plants, animals, fungi, and ourselves. This was one of the most significant events in life's history, unfolding quietly, invisibly, in waters that no eye could see. As we drift slowly through this ancient time, imagine continents barren yet majestic, mountain ranges shimmering under unfamiliar skies, seas rich with microbial bloom, all of it moving with patience, the planet breathing in rhythms beyond human measure. For those of us listening now, wrapped in the gentle cadence of this story, there is comfort in knowing that Earth has always moved at its own tranquil pace. So rest with this vision, an Earth half-formed, learning to breathe, preparing in silence for the future. And as we leave this first chapter of the Proterozoic, one wonders, what other secrets lay hidden in the endless patience of deep time, waiting for us in the next. Oceans deepened into quiet laboratories, their chemistry shifting slowly in the long twilight of the Proterozoic. Here, in waters green with dissolved iron and rich with minerals, life pressed forward in subtle ways. No forests yet whispered in the wind, no insects yet hummed their brief songs. Instead, the world belonged to the unseen, the mats of cyanobacteria spreading across tidal flats, the drifting colonies of algae, the tiny architects of oxygen who were unknowingly preparing the stage for every complex creature to come. Geologists remind us that during this vast stretch of time, Earth's oceans were layered like a cake. The upper waters held oxygen, thin and precious. The deeper layers remained anoxic, filled with dissolved metals and sulfides. To peer into these ancient seas is to enter a place of stark contrasts. A glowing surface kissed by sunlight and microbial blooms, and beneath it, a darker, heavy realm where life persisted in forms we would find alien today. According to studies published by the Geological Society of America, the chemical fingerprints left in rocks show how these oceans slowly mixed, gradually oxidizing over hundreds of millions of years. But perhaps the most enchanting development of this age was the arrival of eukaryotes, cells with internal compartments with nuclei to safeguard their genetic stories. The fossil record tells us that around 16 to 18 billion years ago, the first eukaryotic cells appeared. They were larger, more complex, and filled with potential. Within them lay the seeds of future kingdoms, the branching lineages of plants, animals, fungi. Though still microscopic, they marked a quiet revolution. One of the most fascinating theories about their origin is endosymbiosis. Picture it, a simple prokaryotic cell engulfing another, not to digest it but to live alongside it. This intimate cooperation eventually gave rise to mitochondria, the powerhouses of complex life. Later, some cells took on photosynthetic partners too, becoming the ancestors of algae and plants. What began as an act of survival became an enduring collaboration, one that still powers every breath you take. As oxygen levels continued their slow climb, Earth's atmosphere shifted. The Great Oxidation Event had been the first leap, but oxygen did not remain constant. It ebbed and flowed. For long stretches, levels remained far below today's, but enough to allow these new cellular experiments to take hold. If you close your eyes, you can almost imagine the delicate pulses of oxygen rising like waves, feeding unseen revolutions beneath the waters. Meanwhile, Earth's continents were not idle. They continued their wandering dance, forming supercontinents whose names echo like half-remembered dreams. Nuna, Columbia, Rodinia. These immense landmasses gathered, fused, and broke apart, mountains rising and crumbling in cycles that spanned hundreds of millions of years. As Rodinia assembled around 1 billion years ago, its vast interior may have hosted deserts and shallow seas, places where the first multicellular experiments began. It was around this same time that stromatolites, those microbial monuments, began to wane in abundance. Once dominant across shallow seas, their decline line is thought to reflect the rise of grazers, tiny eukaryotes feeding upon the mats. Here we glimpse another quiet shift, ecosystems becoming more complex, interactions multiplying, the balance of power in the microscopic world evolving, and yet time still stretched like a soft, unbroken melody. To live during the Proterozoic would have meant existing in a world of silence. No birds in the skies, no leaves in the breeze, no footsteps on land. Only the sound of water moving over rock, winds brushing barren continents, and the gentle churn of microbial seas. It is in this silence that we see the profound patience of life. It teaches us that greatness often begins invisibly, nurtured in quiet corners before unfolding into splendor. As we drift with these ancient currents, consider how small beginnings gave rise to everything. Everything, a single engulfed bacterium becoming a mitochondrion, a thin mat of cells building a stromatolite, a faint trickle of oxygen transforming the sky. It is humbling to realize how vast changes emerge from the smallest of acts. If this story of patience and hidden revolution soothes you, remember to like this video and subscribe for more journeys into the forgotten depths of time. The Proterozoic was also a time of color. Imagine oceans stained red when iron met oxygen, settling to the seafloor as rust. Picture skies tinted by volcanic gases, or waters shimmering green with chlorophyll. These were worlds painted in hues no human eye would yet behold. And though beauty is a human word, one cannot help but feel awe at the slow artistry of chemistry and biology combined. By the later Proterozoic, hints of multicellularity appear in the fossil record. Simple filaments, colonies, and clusters, organisms beginning to live not as solitary cells but as cooperative groups. This was another quiet revolution, one that set the stage for creatures of size and shape. But for now, they remain simple, no larger than the width of a fingernail. Still, the principle was there. Together, cells could achieve what none could do alone. The oceans of the Proterozoic invite us to slow down and listen, to imagine life not as sudden explosions but as slow, steady harmonies. They remind us that progress need not be allowed to be powerful. And as we leave these tranquil waters behind, one wonders, in the stillness of those ancient seas, what dreams of future forests and animals were already stirring, waiting for the next. The Proterozoic was not only a time of oceans and microbes, but also of continents restless in their drift. Across hundreds of millions of years, the land masses gathered into immense supercontinents, only to fracture and wander apart again. This cycle of assembly and dispersal is known today as the Wilson cycle, a slow heartbeat of Earth's crust. During the Proterozoic, these cycles became more recognizable, shaping the landscapes that would one day cradle forests, mountains, and the first animal life. The earliest of these great landmasses was Nuna, also called Columbia, which formed about 1.8 billion years ago. Imagine a world where most of Earth's continental crust was fused into a single, sprawling body. Its mountains rose under skies faintly blue, its coasts battered by waves rich in microbial life. Though barren of trees or grasses, Nuna's deserts and rocky highlands were immense in their quiet beauty. Sediments from rivers traced patterns across its interior seas, leaving records that geologists now study as windows into the deep past. Later, Nuna broke apart and another giant took its place. Rodinia assembled roughly 1 billion years ago. Rodinia stretched across the equator, a continent so vast that its interior may have known climates of both dryness and chill. Without plants to anchor soils, wind sculpted dust across the plains. Shallow seas spread across its edges, hosting stromatolites and early colonies of eukaryotes. These were not empty places but laboratories of change, where the chemistry of oceans and atmosphere shifted with every collision of land and sea. Supercontinents left their mark not only on geography, but on climate. As land masses shifted, ocean currents changed. Carbon dioxide levels rose and fell. Glaciations swept the globe more than once. Among them, the great snowball Earth events of the late Proterozoic picture, our planet wrapped in ice glaciers advancing into tropical seas, sunlight reflected into space by endless white beneath the ice. Life endured, but only in refuges near hydrothermal vents beneath thin films of open water, within briny cracks that never froze. These ice ages were extreme yet temporary. Volcanic carbon dioxide eventually built up, thawing the globe in pulses of warmth that may have triggered new bursts of evolutionary creativity. According to studies from the journal Nature Geoscience, the breakup of Rodinia may have played a role in these frozen intervals. As continents rift, Volcanic outpourings and weathering cycles disrupted the balance of carbon dioxide, pushing Earth into climate instability. These changes, though catastrophic in appearance, forged pathways for complexity. When glaciers melted, nutrient-rich waters spread across the oceans, fueling blooms of photosynthetic organisms. More oxygen seeped into the seas, allowing life to experiment with new forms. Meanwhile, the rocks of this era tell stories of mountains taller than the Himalayas, carved down over eons. Erogenous mountain-building events sculpted the crust again and again. The Grenville orogeny, tied to the assembly of Rodinia, raised mighty ranges whose remnants now lie scattered across North America and beyond. These ranges, once colossal, eroded slowly, their minerals washed to sea, nourishing ecosystems invisible to the naked eye. From stone to sediment, from mountain to microbe, Earth recycled itself endlessly. One might imagine these lands as lonely, silent realms. No grass softened the valleys. No mammals roamed the peaks. And yet to stand upon Rodinia, had one been able, would have been to gaze at horizons unbroken by human noise, skies vast and unsullied, stars gleaming as they do now, but with no eyes yet to marvel at them. Such thoughts remind us of how deeply Earth's past humbles us, and how even in silence, beauty endures. As the Proterozoic marched on, life's experiments with multicellularity grew bolder. Fossils like Grippania, a ribbon-shaped organism dating back over 1.6 billion years hint at these steps. Later, red algae fossils appear, among the earliest known multicellular eukaryotes. These were delicate beginnings, mere threads and sheets, but they foreshadowed forests of kelp and coral reefs yet to come. Around 750 million years ago, as Rodinia broke apart, the stage was set for even more profound change. Oxygen levels began to rise again, a second great wave of enrichment sometimes called the Neoproterozoic oxygenation event. With it came the possibility of animals, organisms needing more energy than microbes or simple algae could muster. Though still far in the future, the whisper of complex life stirred in the seas. For now, though, Earth remained a place of contrasts. Frozen white during its glacial extremes and warm, shallow seas during its interludes of thaw. Mountains rose and fell. Continents wandered. Microbial mats built their domes, while eukaryotes learned cooperation. This was a world in slow motion, but each step was essential to the story of life. Pause for a moment and imagine these changes not as distant abstractions, but as part of a continuous flow that leads directly to us. The air we breathe, the land we walk upon, the complexity of our cells, all trace their ancestry to these Proterozoic rhythms. To listen to this story as you drift toward sleep is to remember that patience is the truest force of transformation. And so, as Rodinia breaks and the globe trembles with ice, we are left to ask, in these cycles of cold and heat, of gathering and dispersal, what new wonders were waiting in the next? The late Proterozoic, often called the Neoproterozoic Era, carried Earth closer to the threshold of visible life. By now, oxygen levels had risen to perhaps half or more of modern concentrations, reshaping the chemistry of air and sea. This invisible enrichment was not just an atmospheric shift, it was a doorway. It opened pathways for creatures that demanded more energy, more complexity, more cooperation between cells. For billions of years, life had been microscopic, but here, in the fading centuries of the Proterozoic, the first stirrings of animals began. The evidence is delicate, etched into rocks older than imagination. In Namibia, Australia, and Newfoundland, scientists have found fossils from around 600 million years ago that belong to the Ediacaran biota. These were soft-bodied organisms unlike anything alive today. Some resembled fronds anchored to the seafloor. Others appeared as quilted discs or flattened ribbons. Names such as Dickinsonia and Charnia mark their place in history. Their forms are enigmatic, defying neat classification. Were they early animals, colonies of microbes, a separate experiment in multicellularity, now vanished? The debate continues, but their presence tells us that complexity was blossoming in ways both strange and wondrous. Imagine drifting through shallow seas of the Ediacaran, currents soft, sunlight filtering through water rich with plankton. Upon the sandy bottom, quiet gardens of these organisms swayed, their bodies absorbing nutrients directly from the water. No bones, no shells, no eyes, only simple passive forms attuned to the gentle rhythms of tide and current, a silent prelude to the bustling ecosystems that would later fill the ocean's earlier multicellular forms had already appeared. Simple algae and filamentous colonies, but the Ediacaran biota represented a leap in size and diversity. For the first time, life was large enough to leave visible imprints on the world. Some fossils are preserved as impressions in sandstone, delicate outlines pressed into the ancient seafloor. To look upon them today is to glimpse ghosts of creatures that lived nearly 600 million years before us. Alongside these first experiments in form, Earth's climate remained dynamic. After the great snowball Earth glaciations of roughly 720 and 635 million years ago, the planet thawed, creating seas enriched with nutrients from glacial runoff. According to research from Science Advances, these pulses of nutrient input may have fueled the rise of larger organisms, supplying the oxygen and food needed for bodies bigger than a single cell. It was as if the hardships of ice prepared the stage for life's flowering, a reminder that even in extremity, growth may follow. With oxygen climbing and ecosystems shifting, predator-prey interactions may have begun for the first time. The appearance of burrows and trackways in late Proterozoic rocks suggests that some organisms were mobile, seeking food or escaping threats. These traces are humble, shallow lines in stone, yet they speak of curiosity, of hunger, of survival. They mark the dawn of behavior, not just existence. The continents of this time also carried echoes of change. Gondwana, a vast southern supercontinent, was assembling by the close of the Proterozoic. Its mountain ranges and coastal seas shaped climates that influenced the spread of life. Shallow shelves provided nurseries for microbial mats and early animals, environments stable enough for delicate experiments in multicellularity. And still silence ruled the land. No plants greened the hillsides. No insects stirred the dust. Only wind, rock, and water filled the senses. To sleep upon the shores of Gondwana would have been to hear nothing but the crash of waves and the sigh of breeze across stone. Yet within the seas, unseen revolutions carried forward. What strikes us most about the Proterozoic is its patience. For nearly 2 billion years it was a world of microbes. Only in its final chapters did multicellular life cautiously emerge. The Ediacaran biota may seem fragile compared to the creatures that followed, but they embody the principle of beginnings. They remind us that every forest, every reef, every creature with eyes and in bones stands upon the shoulders of these early, formless pioneers. If this quiet unfolding soothes your thoughts, and the image of frond-like bodies swaying in primeval seas carries you toward rest, consider subscribing to the Faded Clock for more stories of Earth's forgotten ages. These ancient rhythms are not just science, they are lullabies from the planet itself. As the Proterozoic drew toward its close, something extraordinary loomed, the Cambrian explosion, a burst of life forms filling every ecological niche. But before that awakening came the final breath of the Proterozoic, a soft crescendo of oxygen, ice, and strange creatures gliding through shallow seas. And so we ask, as these quilted, gentle beings thrived in Earth's twilight, did they sense the coming dawn of animals with shells, teeth, and motion? Or did they simply sway unaware in the eternal present of the next? The Proterozoic's long silence ends not with a sudden shout but with a steady crescendo. For nearly 2 billion years, Earth had prepared in patience. Oxygen rising, continents drifting, glaciers sweeping, microbes weaving their mats across tidal flats. At last, in its closing chapters, the era gave birth to complexity in earnest, seeding the world with forms that would pave the way for animals, forests, and every beating heart. It is humbling to think that more than 40 of Earth's history unfolded during this era. The very crust beneath your feet, the breath you draw, and the cells that carry your life story are all descendants of transformations begun in those ancient seas. The Proterozoic was not empty. It was not a pause. It was the deep breath before song. Oxygen, once poison, had become a blessing. The atmosphere now carried levels that allowed for larger bodies, tissues, and the stirrings of motion. The oceans, layered for so long, were more thoroughly oxygenated. This change did not happen in a moment but across millions of years. It was a soft, steady unveiling, like dawn stretching across a darkened sky. Life answered. The Ediacaran biota, delicate and strange, filled shallow waters with patterns unlike anything before. Fossils such as Dickinsonia, with its quilted ridges, or Charnia, a frond-like form, were not experiments destined for permanence. Most left no descendants we recognize today. But they matter not for survival but for demonstration, for proving that life could be more than single cells and mats of microbes. They were possibility embodied, fleeting but profound. At the same time, the first hints of animals appear. Simple sponges, perhaps tiny worms, maybe even the earliest cnidarians, creatures related to jellyfish. The fossil record is uncertain, but chemical traces, such as sterins preserved in rocks over 600 million years old, suggest that sponges had already emerged. If true, then the roots of the animal kingdom were already in place before the Cambrian dawn. These small revolutions were matched by great shifts in the planet itself. Gondwana, vast and southern, was piecing itself together. Its assembly marked one of the last great continental arrangements of the Proterozoic. Mountains rose where plates collided. Rivers carried their sediment to the sea, feeding microbial blooms. Glacial scars on its rocks tell of cold intervals, reminders that even as life advanced, Earth's climate remained a force of trial and transformation. And then, on the horizon of time, the Cambrian explosion awaited. Around 541 million years ago, the curtain lifted on an age of shells, cells, spines, eyes, and motion. The fossil record bursts with trilobites, brachiopods, mollusks, and the earliest vertebrate-like forms. It was a proliferation so sudden geologically speaking, that Charles Darwin himself once marveled at its abruptness. Yet when seen through the lens of the Proterozoic, it was not abrupt at all. It was the flowering of seeds planted in 2 billion years of patience. The Proterozoic gave us more than fossils. It gave us the blueprint for complexity. Eukaryotic cells born of symbiosis became the foundation of all higher life. Oxygen drawn from the quiet work of cyanobacteria transformed the atmosphere into a breathing sky. Continents, colliding and breaking, set the stage for ecosystems by shaping climates and seaways. Ice ages, brutal and encompassing, tested life's resilience and enriched the oceans with nutrients. Each of these threads wove the tapestry from which modern Earth emerged. Today we walk in forests that root in soils once barren. We breathe air forged by the labors of ancient microbes. We gaze at oceans alive with whales and coral reefs, knowing they are built upon foundations laid by stromatolites and algae billions of years ago. The Proterozoic lives on in every cell with a nucleus, every breath rich in oxygen, every stone that carries the whisper of iron and rust from an ancient sea. As you rest, allow yourself to drift with this thought, that the Earth you know is the child of patience, that silence and stillness, stretched across unimaginable time, were not empty, but full of preparation. That every dawn we witness carries within it echoes of a far older dawn, when oxygen filled the sky and strange fronds swayed in shallow seas. If this journey has carried you towards sleep, let it also carry gratitude for the slow artistry of the planet, for the quiet persistence of life, and for the reminder that transformation does not always roar. Sometimes it simply waits and unfolds. If these ancient stories bring you peace, subscribe to the faded clock to wander with us again into the timeless past. And so, with the close of the Proterozoic, we leave behind a world still silent on land, but alive with promise in the sea. A world ready for the Cambrian's bloom. A world that across 2 billion years of quiet change had prepared the way for everything we know. And as the stars rise over that ancient ocean in your imagination, one last question lingers. If patience built the earth we stand upon, what patience might we learn to carry into the next? Thank you for drifting through this journey with the faded clock. If this story of ancient Earth soothed your mind and eased your rest, consider subscribing, liking, and sharing so more dreamers can wander into the past with us. Until our next voyage through deep time, may your nights be calm and your thoughts as vast as the eons.